Hello, everybody. Today we're going to finish up talking about the reactions of the alkenes, and then we'll push on to our next family of reactions, which will be nucleophilic substitution and elimination, and that will close out the curriculum for the term. So the final exam next Wednesday is looming large for us. I posted a practice final exam on the course website, so please check in. And I will be having my usual office hours on Sunday afternoon at 2 o'clock in case you have any questions. And then I will also have an additional office hour Monday night at 7 p.m. And then the final is Wednesday. Monday is the last lecture. There is no lecture on Tuesday, but I believe that your discussion leaders will be having a final exam review during the lecture meeting time. The normal discussion is on Wednesday, of course, so there won't be any next week. It will be after the final, but I'm pretty sure your discussion leaders are going to organize some sort of review during the lecture meeting time, but I hope that they are in contact with you about their plans for a pre-final exam. All right, so going to finish up talking about the reactions of the alkenes, and we only have one more reaction to talk about, and that is hydrogenation. Of the alkene. This is a very important reaction, not only in the organic chemistry laboratory, but also in industrially, because I'm sure you have all heard of hydrogenated oil, which is one of the things that finds its way into all kinds of highly processed food. Well, that hydrogenation, that is this reaction in action. We'll talk a little bit more about the industrial uses of hydrogenation. Let's talk about what this reaction does and its mechanism first. All right, so in hydrogenation, the overall reaction involves an alkene reacting with hydrogen in the presence of a metal catalyst. And this reaction has some very expensive tastes. I can tell you that, because the catalysts that are used here, although many things have been tried, the catalysts that are most used here would be platinum, which is more expensive than gold, and palladium, which is also extremely expensive. All right, so what happens in this reaction is that the carbon-carbon double bond is degraded to a single bond, and the atoms of hydrogen add across where the double bond used to be. So it is the taking down of a carbon-carbon double bond to a carbon-carbon single bond. All right, bullet points for the reaction is, the important information that I would like for you to know about this, besides the mechanism that we'll talk about in a minute, is that this is the new H's are delivered to the less hindered side of the original alkene. And this is a theme that we've seen repeatedly in many reactions, so this is nothing new. the two hydrogens on the less to the less hindered side. And another thing to keep in mind is that this is a cis addition. And again, we've seen this characteristic of many reactions where those two hydrogens are going to come in on dashes, both of them. They're going to come in on wedges, both of them. They're going to come in from the top of the molecule or the bottom of the molecule. So this is nothing new. And these two characteristics of this reaction are explained by the reaction mechanism. Okay, so let's do some problems before we talk about the mechanism. Because all we really need to know to figure out the products is this. All right, so what if we were to take styrene and react that with hydrogen in the presence of palladium? What are we going to get? That double bond is going to be taken down to a single bond. So this is pretty easy. We just get the styrene is converted into ethyl benzene, where we've added two hydrogens across where that double bond used to be. All right, but let's try something a little bit more challenging, which will be the where some of the stereochemistry is involved. So one of our favorite reactants is this guy here. And what if we were to react him with hydrogen in the presence of a platinum or palladium catalyst? Draw the structure of the molecule, draw the structure of the product. Well, we've seen this system or something like it several times already. And we know that that methyl group in the 9 position, that's this one up here, this methyl group in the 9 position that's on a wedge, he is inhibiting the reaction from the front of the molecule. So the back of the molecule is the less hindered side, and that's where the hydrogen is going to end up. And the hydrogen is also delivered in a cis manner. So the product here will be this double bond got knocked out. A new hydrogen came in from the back. So I'm dashing him. And this pre-existing methyl group down here at the 2 position, he got shoved to the front because a new hydrogen came in from the back. So I don't have to represent that second hydrogen. All I have to do to communicate the fact that there's now a new hydrogen that wasn't there before on this carbon here at the 2 position is to wedge what was the pre-existing methyl group, so that there's a new hydrogen there, of course, and he's on a dash in the back of the molecule. All right, so let's see, let's just try maybe one more. What about maybe something like this? I like this molecule. Hydrogen and maybe a palladium catalyst this time. Draw the structure of the product, dash and wedge all the chirality centers. Okay, so maybe we've seen this molecule already as well. So tell me in the chat here, is the hydrogen going to come in on dashes, or is the hydrogen going to come in on wedges? So tell me in the chat here, hydrogen on dashes, hydrogen on wedges. Uh-oh. Well, had a 50-50 chance of being right just by guessing, but fortune did not favor anyone who has answered so far. The new hydrogen is going to come in on dashes because the back of the molecule is more sterically accessible than the front. The back of the molecule is just defended by these 2 teeny tiny hydrogens. The front of the molecule has this big dimethyl cyclopropyl moiety. So it's going to be very difficult to approach from the front. Instead, the hydrogen is going to come in from the back. You know, one of the skills that we worked on is translating a chair to a flat drawing and vice versa. Well, if you did that to something like this, you would see that this dimethyl cyclopropyl moiety is sticking up. And so it's the back that is going to be more reactive, because the back has the less sterically hindered side. Okay, so that double bond got knocked out. It became a single bond. Originally, there was only one hydrogen here at the 4 o'clock carbon. Now there are two. But when we write a bond line structure, we don't need to write hydrogens necessarily, so I won't do that. A new hydrogen came in here at the 2 o'clock carbon, but he came in from the back, flinging the pre-existing methyl group at the 2 o'clock carbon to the front. So that methyl group is now living on the wedge. Okay, so that would be the product of that reaction with its stereochemistry shown. All right, so let's talk about, oh, before we do that, how about let's look at some pictures. Oh shoot, that's not what I want. This is what I want. Okay, so here I made one of those Avogadro models of this molecule. This is kind of similar to the problem that we just did. And what we see here, that stick-up methyl group here, we see that stick-up methyl group, and it is impeding the approach from the front or from the top here. This yellow line right here, that's where the double bond is. And so this molecule, it's much easier for a reagent to approach from the bottom in this Avogadro model, or from the back in this bond line representation. All right, the molecule we just worked with had that dimethyl cyclopropyl moiety. And so here's a model of this molecule where, once again, the double bond is, the position of the double bond is indicated by this yellow bar here. And we see that dimethyl cyclopropyl moiety is hanging over the double bond. It's just much easier to come in from the bottom of this model here, or from the back of this model here. All right. Okay, let's talk about mechanism of hydrogenation. All right, we begin with the catalyst, which will be platinum or palladium. So what exactly that is you have a surface, the metal surface, and on the surface you have just, you know, a gazillion platinum or palladium atoms. I don't have time to draw a gazillion of them, but I will draw many. So that's what the surface of the catalyst is looking like. It's just a sea of platinum atoms that are exposed to the reactants. Okay, so I'm not going to have time to write that over and over and over again. So let me just abbreviate it in this way. So that's the catalyst. Surface. And what I'm implying by that is that the top layer of this catalyst has a bunch of platinum or palladium atoms. So I start with my catalyst and I dose it with hydrogen, which of course is going to be in the gas phase. The hydrogen undergoes a reaction called dissociative adsorption, where the hydrogen-hydrogen bond breaks in a homolytic way. In other words, one atom of hydrogen gets one electron, the other atom of hydrogen gets the other electron, and now those hydrogen atoms bond to the platinum or to the palladium on the surface of the catalyst, because those metals have a low-lying, half-filled d orbital. Remember d orbitals from Gen Chem? So there is this dissociative adsorption where now the hydrogen is stuck. It kind of looks like two flowers growing out of the soil. They used to be bonded together, but now that bond, hydrogen-hydrogen bond broke, and now hydrogen is forming a bond to an atom of platinum or palladium on the surface. This is called dissociative adsorption. Adsorption, because the hydrogens are now stuck, they are adsorbed to the catalyst surface. Dissociative, because this hydrogen-hydrogen single bond was degraded one notch to a zero bond. These hydrogens aren't bonded together anymore. So that's why it's called dissociative. The hydrogen atom dissociated. All right, so that's how we can represent this first event in the mechanism, but we would like to also rewrite this in a more grown-up, conventional way. And so we would do that maybe by saying, same thing would be, we have a hydrogen in the gas phase, and now we dose the platinum or palladium surface. Let's just use palladium. And the bond breaks in such a way that now we have hydrogen atoms or hydrogen radicals adsorbed to the surface of the metal. But these are not free radicals in that they're not whizzing around in three-dimensional space as if they were in the gas phase. These hydrogen atoms are stuck to the surface of the catalyst, of the palladium. Okay, and so now it's time for the alkene to get involved, and the alkene is also going to do a dissociative adsorption. So let's say if we represent the alkene like this. And so now the alkene also undergoes dissociative adsorption, where this double bond gets degraded to a single bond, and the bond breaks homolytically. One carbon atom gets one electron, and the other carbon atom gets the other electron. And so now our surface is going to look like this, where we have a hydrogen over here, and now the alkene double bond was degraded to a single bond, and we have a hydrogen over here. All right, and so once again, that is dissociative, is that double bond of the alkene got taken down one notch to a single bond, just like the single bond of the hydrogen got taken down one notch to a zero bond, to a bond that didn't exist anymore. Okay, so the alkene then undergoes this dissociative adsorption on the catalyst surface. All right, so let's write a chemical equation that describes that same event. So we would have the alkene, and he comes into contact with the catalyst surface. We get dissociative adsorption. That carbon-carbon double bond breaks homolytically. Each of the carbon atoms gets one electron of that bond, and this is stuck to the catalyst surface. Well, so, you know, this hydrogen, does he have a noble gas configuration? Is he isoelectronic with helium? No, he wants an electron. What about this carbon here? Is he very happy? Well, he's a radical, right? And so to finish this mechanism off, what happens is you have all of these species running around on the surface of the catalyst surface, they just team up. These dots team up. Kind of looks like a radical reaction. It is, but these are surface adsorbed radicals. And so one of the hydrogen flowers gets picked by the alkene, and then the other hydrogen flower gets picked by the adsorbed alkene. And so what has happened here is the hydrogenation of that carbon-carbon double bond to a single bond on the surface of the catalyst. And now this thing is going to diffuse away from the surface of the catalyst. It could enter into some kind of side reaction, but that's not normally a problem. Okay, so that's our mechanism for hydrogenation. All right, so let's see, maybe let's look at some pictures. All right, so I have a sequence of pictures here that just illustrate what I talked about. There's the surface of the catalyst. There's the hydrogen. It got adsorbed. And now the alkene is also going to get adsorbed on the surface. And so here's that the alkene is indicated by those red atoms, and it's going to lie down on top of the catalyst surface. But this alkene has that stick-up methyl group here, which is impeding the approach of the alkene to the catalyst surface. If I flip this guy over and bring the methyl group closer to the catalyst surface, we see that these red atoms here, that's where the alkene is, very, very far away. These two atoms are not going to be able to stick effectively to the catalyst surface. So that's why hydrogen enters in, is delivered to the less hindered side, because everything has to, the alkene has to be stuck to the catalyst surface, and it's going to be the less hindered side of the alkene, which is more readily accessible. So we talked about how this reaction is, it's a controversial reaction. It's also an important reaction industrially. So here we see the lumen of an artery that is being clogged by LDL, bad cholesterol. And what this plug is made out of is saturated fat. A saturated fat means a fat that has no double bonds in it, just single bonds. And so, you know, lots of food contains this saturated fat. Butter, 69% saturated fat. That's probably why it's so good. Whale blubber, about 55% saturated fat. You know, we're told we're told not to eat saturated fat, but the ethnic group, which is now called Inuit, their diet is made up of huge amounts of saturated fat, because what they eat is seal blubber and whale blubber. That's what some of the principal foods of the Inuit people, but they have very low incidence of heart disease. So it must be genetically determined. Why do we have so much heart disease from eating saturated fat, but other people don't? Okay, so whale blubber is 55% saturated fat. Human fat is about 45% saturated. All right, and olive oil, this is only 10%, right? So you're supposed to eat these healthy oils that are low in saturated fat. Saturated fat means no carbon-carbon double bonds, just carbon-carbon single bonds. And what I have here are some models of saturated fat. This is saturated fat here, where all of these are all carbon-carbon single bonds here. And we see that the molecule is sort of like a pencil or a hot dog, a stubby hot dog or something like that. The cylindrical shape of the saturated fat molecule, that's why it is a solid at room temperature. See this? See that? That's all solid at room temperature. That's saturated fat. These rod-like saturated fat molecules can pack together very efficiently. That's why it's a solid at room temperature. Now, a cis unsaturated fat, this has double bonds in it. This is like the sort of fat that is in olive oil and canola oil and oils of that nature. And it's anything but rod-like, because the double bond in here is cis. And so we see that distinctive V shape of the cis double bond. Here it is again, here it is again. And so these molecules are liquids at room temperature because they cannot pack efficiently, because they are not, the molecular geometry doesn't allow for that. And so that's why things that have a lot of unsaturated fat are liquids at room temperature. And maybe you've heard of trans fat, right? This is supposedly very bad as well. It tastes very good. Studies have shown. So trans fat has double bonds in it, but those double bonds are trans. And so the molecule is sort of, well, it's not as perfectly rod-like as a saturated fat molecule, but it's getting there. So a trans fat can also be a solid at room temperature. And so that's the reason that the food industry takes unsaturated fat and converts it into saturated fat. The reason that the food industry hydrogenates fat is because we've just spent several lectures talking about how the carbon-carbon double bond is reactive, right? We see all kinds of reactions of the carbon-carbon double bond, so that this reactivity of the alkene leads to a much higher probability that that unsaturated fat, that liquid fat that is found in olive oil, for example, is going to go rancid. It's going to, those double bonds are going to react in some way. So the strategy that the food industry employs is just get rid of those double bonds. You're going to get a much less reactive molecule. So that's why that's why a lot of this unsaturated fat is converted into saturated fat, simply to extend the shelf life of the of those compounds, of the fat, shelf life of the product that has those fats in them. Okay, so that's the end of the alkene reactions. And so now I want to start off talking about our new family of reactions. And this will be the final group of reactions for the term. And this is the nucleophilic substitution and elimination complex of reactions. Okay, so starting off this new topic, nucleophilic substitution. All right, so the overall reaction, RXN means reaction. The overall reaction is we have an sp3 hybridized carbon, and it has to be sp3. It can't be anything else. It can't be a carbon atom that is part of a benzene ring. That's sp2. It can't be a carbon atom that is part of an alkyne. that is sp. It must be an sp3 hybridized carbon, and that sp3 hybridized carbon has a halide on it. This guy here, this is called the leaving group because, as we will see, it leaves. There are many kinds of leaving groups in organic chemistry. And if you're around for Orgo 2, you will undoubtedly be meeting more leaving groups. But for right now, all we can confine ourselves to is the halide as a leaving group. Okay, this molecule is called the substrate. It's an sp3 hybridized carbon bonded to a halide, which is the leaving group. Okay, the other actor in this drama is the nucleophile, which I'm going to abbreviate just as nuke. And there are many, many kinds of nucleophiles. We talked about what a nucleophile was, something that's electron rich, that has an electron pair available for bond formation. There are neutral nucleophiles, but many are negative. So what I'm going to do here is I'm just going to represent this as a negative nucleophile, but please bear in mind that some nucleophiles are neutral, right? But just to make this more, what I think is more understandable, let's go with a negatively charged nucleophile. What happens in nucleophilic substitution is the nucleophile ends up on the carbon that used to host the leaving group, right? That's why it's called substitution, because the nucleophile takes the place of the halide, and the halide departs the substrate with the electron pair with which it was formerly bonded to that sp3 carbon. So the actors in this drama are the substrate and the nucleophile. The product of the reaction is the substitution of the halide on the substrate by the nucleophile. Okay, so there I've written out the neutral version, but I guess it wouldn't be too bad if we were to try the, here I wrote out the negative version. I mean, let's write out what the neutral version would look like. The nucleophile would have a proton on it, but the very same thing is going to happen. The nucleophile is going to end up on the sp3 hybridized carbon that used to bear the leaving group, and the halide is ejected, but under these neutral conditions, it's not going to be X minus that is ejected, it's going to be HX. So that's what nucleophilic substitution is. You have an sp3 hybridized carbon bonded to a halide, you hit it with a nucleophile, the nucleophile replaces the halide. Now, we've spent all kinds of time talking about how to put halide on stuff. Radical chlorination, bromination, NBS, HBr and peroxides, reacting an alkene with HX. You know, we spent a whole lot of time talking about how to put halide on stuff. And the reason we have done that is because the halogenation of an organic molecule, that is our entree into nucleophilic substitution. We can't do nucleophilic substitution in the way we're going to do it unless we have halide on an sp3 hybridized carbon. So much of what has gone before has been leading up to this moment. The implementation of an organic halide in this important nucleophilic substitution reaction. And why nucleophilic substitution, why anyone would care, is that nucleophilic substitution provides is the entree to a huge variety of functional group interconversion. So, for example, if we were to take styrene, and we were to react this with HBr in the presence of peroxides, right? What would we get? We would get that we would get Br on the less substituted carbon, right? And so this is what we need for nucleophilic substitution. We need halide on an sp3 hybridized carbon. The virtue, the value of nucleophilic substitution is now, once that halide is on there, we can do all kinds of chemistry, nucleophilic substitution chemistry, in which that Br is going to be transformed into all kinds of other functional groups. All we need to do is react this with a nucleophile, and that nucleophile is going to push out the leaving group, and it's going to end up where the leaving group used to be. So I'm just going to make like a wheel of all of the possibilities, trying to emphasize what nucleophilic substitution is good for. So we could react this bromide with hydroxide. There's the leaving group, there's the nucleophile. What happens is the nucleophile takes the place of the leaving group. Oh, so this is a way of making an alcohol from an alkene, and notice in this two-step procedure, the OH ends up on the less hindered, the less substituted carbon of the original alkene. It's a two-step procedure, and so if we want this molecule, we could either do that hydroboration oxidation, or we could halogenate and then do nucleophilic substitution. So another thing we could do, emphasizing the scope, the enormous scope of nucleophilic substitution, is that we could hit this halide with this alkoxide. This would be a Williamson ether synthesis, and this is a way of making an ether from an alkene by this two-step procedure. First put on a leaving group, first put on halogen, then knock the halogen off with the leaving group. So we've gone from an alkene to an ether. Another thing we could do is react this with yet another nucleophile. How about this acetate? Oh, that's a nucleophile. I see a negative charge on this oxygen atom. And so that would be a way that we could create an ester from something that was 2 steps ago was an alkene. So lots and lots of functional group transformation becomes available with nucleophilic substitution. That's why this reaction is important. Okay, how about reacting our alkyl halide with cyanide? Well, that would be a way that we could make a nitrile from something that was originally an alkene 2 steps ago. You know, just lots and lots of stuff here. How about reacting this with a thiolate? The sulfur atom, that's the nucleophile. It's going to kick out the leaving group. So this would be a way of making a thiol. So when we were talking about halogenation, we never talked about fluoridation, and we never talked about iodination. We said that fluorination, that is very hard to control. That leads to an explosion when we try to do it the way we do chlorination and bromination. And we didn't talk about iodination except to mention that it doesn't work because the activation energies of that first propagation step are very, very high. But with nucleophilic substitution, now we know how to put I on stuff, because all that we would need to do here is now react this alkyl bromide with I minus, that's the nucleophile, and we would end up with an iodinated material. So this is why nucleophilic substitution is worth talking about, because we can do once that halide is on there, we can potentially do all kinds of chemistry, leading to the formation of all kinds of functional groups. All right. So there are two flavors of nucleophilic substitution, and they are called SN1 and SN2. So there are two different nucleophilic substitution mechanisms. I want to talk about SN2 first of all, because that's the more useful, the more reliable, the more easily controlled of the two nucleophilic substitution mechanisms. So there's SN1 and there's SN2. Let's talk about SN2. Okay, so the most important thing about SN2 is that it is it's a one-step mechanism. The nucleophile enters and the leaving group leaves simultaneously. So SN2 one-step mechanism. Nucleophile comes in, leaving group leaves more or less simultaneously. If we wanted to write out an arrow pushing mechanism, we could maybe do something like that. There's the nucleophile. I've given it a negative charge. It could be neutral. I've given it a negative charge. And here is the substrate. Then the nucleophile comes in and the leaving group leaves all in one step. The transition state is going to look like there's the bond that the nucleophile is forming with the substrate carbon. Here's the bond of that the substrate carbon is breaking to the leaving group. The leaving group is leaving, and then the three pre-existing groups were there. So that could be the transition state where we're just showing bonds that are being formed and bonds that are being broken. The product of this reaction, the nucleophile, has ended up on the carbon atom where the leaving group, where the halide used to be. And one of the things I believe in is charge conservation. So I see I have to revisit my transition state and note that the negative charge on the nucleophile, that's going away. It came in negatively charged, but in the product, the nucleophile is going to be neutral. And the negative charge on the leaving group, that is in the process of being developed at the transition state. So this makes, these partial charges make total sense here, because the reactants have an overall -1 charge. The products have an overall -1 charge. The transition state had to have an overall -1 charge, but in this case, it's distributed between two different atoms, of the nucleophile and that of the leaving group, and expressed as these partial negative charges. Okay, so that's the SN2 mechanism. Pretty simple. Nucleophile comes in, leaving group leaves, all at the same time. All right, so let's talk about the energy diagram. Tell me in the chat, how many hills? I want to draw the energy diagram of the SN2. How many hills in the SN2 energy diagram? Anyone giving it a shot out there? I want to draw the energy diagram of the SN2. How many hills? Oh, it's going to have one hill, because if the reaction mechanism has one step, it's going to have one hill. The reactants live in a valley. The transition state lives on the top of that hill. The products live in a valley as well. So one step mechanism means one hill in the energy diagram. So there's the energy. This is the reaction coordinate down here. And here is the reactant valley, where we have the alkyl halide and we have the nucleophile here. And over here, we would have the product valley. A lot of these SN2 reactions tend to be approximately thermoneutral. So the reactant frequently, if you did a bond energy calculation, frequently the product would be about the same energy as the reactant. So a lot of these reactions are thermoneutral. Some of them aren't, but so we're not going to draw the product valley way the heck up here. We're not going to draw the product valley way the heck down there. So we have the product valley here. And what has happened is the nucleophile ends up on the carbon atom where the leaving group used to be, and we have one hill. And now, because the reaction many of these reactions are approximately thermoneutral, the Hammond postulate doesn't apply. But we can connect these two guys, these two valleys, kind of missed, with our one hill like this. And who lives up here? The transition state, where bonds are in the process of being broken and being formed. So there's our transition state up here living at the top of this valley. Okay, so that's what the SN2 diagram, energy diagram looks like. All right, so one of the things that we're getting out of this energy diagram is that we can write the rate expression for the SN2 reaction. The rate of the reaction, the rate of SN2 is going to be equal to some rate constant. But because it's a one-step mechanism and because the transition state, the substrate and the nucleophile have to interact, they have to crash into each other in order to achieve the transition state, the rate of the SN2 reaction is going to depend on the concentration of substrate and the concentration of nucleophile, right? It's not going to be just, the rate isn't going to depend just on the concentration of substrate, because the substrate has to crash into the nucleophile in order to get a reaction. The rate isn't going to depend just on the concentration of nucleophile. It's going to, because the nucleophile has to crash into the substrate in order to get a reaction. It's going to depend on both of them. So this is what that 2 means. This 2 means that the reaction is bimolecular, meaning that 2 things, a nucleophile and a substrate, have to get together. The S means substitution, the N means nucleophilic. So that kind of explains where this name SN2 comes from. So the most important thing about SN2, it's a one-step mechanism. That one-step mechanism has several implications and ramifications, which I'm going to get into after my break. All right, so my computer says 9:50. I'll be back at 10 o'clock. Okay, hello once again, everybody. So continuing to talk about the consequences of that one-step mechanism, we just saw the energy diagram and the rate expression. Another consequence of the one-step mechanism would be the stereochemistry. I can't write. Stereochemistry of SN2, described as backside attack, meaning that the nucleophile is coming in the back door as the leaving group, the halide, goes out the front door. And this happens for various reasons. We can explain it by a molecular orbital approach. We can also explain it on steric grounds. So for example, the nucleophile attacks the substrate carbon, sp3 hybridized, in this backside manner, so that if the nucleophile, if the leaving group were in the front of the molecule, the nucleophile is going to come in from the back. If the leaving group is on a dash, the nucleophile comes in on a wedge. So this is a characteristic of the SN2 reaction, this backside attack. And remember, this has gone through a transition state where the nucleophile is coming in the back door as the leaving group leaves out the front. So the transition state looks like this. Right, that's backside attack versus front side attack, which would be much more sterically hindered. So here we have an example of front side attack where the nucleophile is coming in the front door as the leaving group tries to exit the front door as well. So that would be the transition state for what we'll call front side attack. And we see that this transition state is wrong for all kinds of reasons. First of all, it's much more sterically hindered than the backside attack. The nucleophile is trying to come in the same orientation that the leaving group is trying to leave. So these two groups are going to be abutting each other here, causing all kinds of steric hindrance. Another reason that this front side attack is all wrong is because negative hates negative. And we have these partial negative charges clustered together closely here in the front side attack transition state, whereas in the backside attack transition state, the two partial negative charges are as far away as they can be from each other. So we never see front side attack in the SN2 reaction. We always see backside attack. Okay, so let's do some problems. What if I had this guy and I want to react him with acetate? So draw the structure of the product and dash and wedge all of the chirality centers. Well, the BR is in the front on a wedge. The nucleophile is going to come in from the back on a dash. So this is a very nice feature of the SN2 reaction, because we have a lot of control and a lot of reliability concerning the stereochemistry of the product. When we get into the SN1, we see that this doesn't happen in the SN1. That's why SN1 is not as useful as SN2. All right, so I have a couple of things to say about this example here. Is that that's the substrate. How do I know that? I see an sp3 hybridized carbon bonded to a leaving group. That's the nucleophile. How do I know that? Well, it has an electron-rich, this negatively charged atom. Every nucleophile has a nucleophilic atom, and that's what the nucleophile uses to bite into the substrate. So notice this oxygen atom with a negative charge, that's what ends up bonded to the carbon that used to have the leaving group. So like on that final exam for next week, I'm going to mark wrong a bunch of stuff that does not comprehend that principle I just talked about. So something like this, if you were to write something like this, CH3S minus, that's the nucleophile. Every nucleophile has a nucleophilic atom. In this case, it's sulfur. But what if on that final exam, you write something like this? Okay, you understood about the dashing and wedging, about the stereochemistry, but you didn't understand what the nucleophilic atom was, right? Yes, the nucleophile ends up on the carbon atom that used to have the leaving group, but it is the nucleophilic atom of the nucleophile. Many times this is going to be the negatively charged guy that ends up biting into what used to be the substrate carbon. So something like this, just going to have to mark this wrong, right? Should be should be something that looks like this, where that sulfur atom attacked and displaced the leaving group. All right, so that's pretty simple. How about let's try something a little bit more complicated. Let's get back into chairs. All right, so there's our substrate. That could be our nucleophile. Draw the structure of the product. Give me a chair conformation. Tell me in the chat, what about that? What about this SCH3 group? Is he going to be axial or is he going to be equatorial? So I want a chair conformation here. Tell me about that CH3S. Is he going to be axial or is he going to be equatorial? Oh, he's going to be axial, right? Because the nucleophile comes in the back door as the leaving group goes out the front door. So the S minus attacks here, kicks out the I minus. What would the transition state look like? There's a hydrogen atom there. And here we see the nucleophile coming in from the top as the leaving group leaves from the bottom. There was a hydrogen there, right? There always was. This is the transition state for the SN2. And we see that the product here is going to have the axial, the nucleophile will be axial. So we know that being axial is bad, right? So this is the orientation of the nucleophile at the instant right after the reaction, but we know that chairs interconvert. And so this is going to be an equilibrium mixture, right? But at the moment that the nucleophile comes in, that nucleophile is going to be axial, and then the thermal, and then it's going to do this chair flip, and so we'll get both of these present. Okay, so maybe someone here has an instructive question. Why wouldn't it just be the S added? Because every nucleophile has a nucleophilic atom. And in this case, the nucleophilic atom is S. The displacement, the thing that goes away, is the halide on the substrate, not any part of the nucleophile. So this S minus is dragging along this methyl group. The thing that goes away is the halide on the substrate, not any part of the nucleophile. So I hope I answered that. Okay. So that's another consequence of that one-step mechanism, the stereo chemistry. All right, another consequence of the one-step mechanism is, let's look at the substrate structure. The nucleophile has to get in there and push the halide out in one step, so that if the nucleophile has trouble getting into the substrate carbon, that is going to slow down the reaction. So we see a very nice correlation between the rate of an SN2 reaction and the structure of the substrate. Crowding at the substrate carbon retards, slows down the reaction. RXN means reaction. So the best kind of substrate for an SN2 reaction is a 0 degree primary, it's a 0 degree super primary or methyl substrate. That is fastest in an SN2. Why? It's the least crowded. The nucleophile only has to fight its way past 3 teeny tiny hydrogens to push that leaving group out, right? In this one-step mechanism, the nucleophile has to push out the leaving group. But now when we start to junk up the substrate carbon with big bulky groups, there's a primary. That's not as good, because now the nucleophile has to fight its way past a much bigger methyl group. And then when we junk up the substrate carbon even more, making it secondary, the reaction is even slower. And then when we junk it up even more, making that substrate carbon tertiary, now the reaction doesn't happen at all, right? Never. We never see an SN2 reaction on a tertiary substrate. Why? It's just too crowded, right? So effectively, the SN2 doesn't work on a tertiary substrate. A secondary substrate would be the slowest kind of substrate that we can ever see in an SN2 reaction. And the reason for this is because the nucleophile has to push the leaving group out from the substrate. And if the substrate carbon is too crowded, the reaction just slows down. And with a tertiary substrate, we never see an SN2 reaction on a tertiary substrate. So that's another consequence of the one-step mechanism, is the substrate structure. Okay. Next, let's talk about the nucleophile structure. the nucleophile has to push the leaving group out so that the types of the typical SN2 nucleophiles are what are called so-called good nucleophiles or powerful nucleophiles. The nucleophile must be a quote unquote, I'll define this term here in a second, must be a good nucleophile. It has to push that leaving group out. So it has to be a powerful nucleophile. It has to have high nucleophilic ability or high nucleophilicity. And what exactly a good nucleophile is, so let's try to define that. A good means, first of all, anionic, right? Is that water is neutral. Water is a lousy nucleophile. OH minus is a much better nucleophile because a nucleophile is something that's electron rich, and something that has a negative charge on it is going to be a better nucleophile because it's more electron rich than something that is neutral. So something like this, OH minus, is better than H2O. And in fact, water, this probably not be a very effective SN2 nucleophile at all because it's neutral. So that's one of our demands that we make on the nucleophile, that it be a powerful nucleophile, and one of the criterion will be that it is anionic. Okay, another characteristic of this good nucleophile is that it is a strong base. All right, at that makeup lecture, we talked about what exactly a base is. A base is a proton acceptor. And we talked about a base strength as measured by the pKa. So that when we talk about a strong base, what we mean by strong base is that the pKa of the conjugate acid this is going to be something like less than or equal to about 14. Strong base, pKa of the conjugate acid is, let's see, do I want to say 14? Greater than or equal to about 14. Okay, so let's unpack what we've said here. Is that something like this, CH3 minus, that could be an SN2 nucleophile. I see it's anionic. And the pKa of the conjugate acid, which is methane, that's about 50. Oh, so this is a very powerful base. The pKa of the conjugate acid is way over this dividing line of 14. So that's an excellent SN2 type of nucleophile. It's anionic. It's also a very powerful base. Something like an alkynyl anion. Is that a good SN2 nucleophile? Oh my heavens, yes. It's anionic, and the pKa of an alkyne right? I'm going to write the conjugate acid here in brackets. That's what the conjugate acid looks like. The pKa of an alkyne is about 25. So this is going to be a great SN2 nucleophile. It is anionic and it's also a strong base. All right, so something like methoxide would be another example here. That's a good SN2 nucleophile. Its conjugate acid is methanol, pKa about 17. But now when we get down to something like, acetate, the conjugate acid here is going to be that. The pKa of the conjugate acid is 5. So this is an okay, this is just barely an okay kind of nucleophile. It's not as good as any of these others, so that we see that a reaction using acetate is going to be much slower than one that's using methoxide. So the typical SN2 nucleophile is going to be anionic, and it's going to be a strongly basic nucleophile. And those two criteria make up what we call a good nucleophile or a powerful nucleophile. But the truth is so messy, right? But, and it's a big but sterically hindered bases are poor nucleophiles, regardless of basicity. In the SN2 reaction, the nucleophile has to get in there and push the leaving group out. If the nucleophilic atom is junked up with all kinds of fishtails and chicken feet and benzene rings and all of this stuff, the nucleophile just can't get in there to push the leaving group out. It's just too crowded. So we have a stereotypical set of stuff that we can think of as sterically hindered bases. So one of them that we see very frequently is this guy, tertiary butoxide. This is a sterically hindered base. It's a bad nucleophile. It's a terrible nucleophile because the nucleophilic atom is junked up with this chicken foot. The nucleophile can't get in there to the substrate carbon and push the leaving group out. The pKa of the conjugate acid here is 17. That's beyond our 14 dividing line, right? So this is a pretty powerful base, but it's a terrible nucleophile because it's sterically hindered. Another stereotypical strong base, but which is a terrible nucleophile, would be this diisopropylamide anion. The pKa of the conjugate acid here is 35. That is an extremely powerful base, but it's a terrible nucleophile because the nucleophilic atom is in a crowded environment. It is just too crowded to get in there and push the leaving group out. Another very powerful anionic base, which is a terrible nucleophile, would be the triphenylmethide. So something like this with all of these benzene rings. I'm going to make this carbon negatively charged. It's anionic. The pKa of something like this, of the conjugate acid, is about 50. That is anionic. It is a powerful base. It is a terrible nucleophile. It's just too crowded to get in there. to function as the nucleophile. So the typical SN2 nucleophile is anionic and strongly basic, but it can't be sterically hindered as well. Continuing to talk about how the truth is so messy, big atom nucleophiles are good nucleophiles, regardless of basicity. And what big atom means is third row or lower on the periodic table. Big atom, this means the atomic number of that atom is greater than 10, right? So some of the big atom nucleophiles, some nucleophiles that are good nucleophiles for SN2 that fall into this category would be Cl minus, right? That's on the third row of the periodic table. It's anionic, but if you look at the pKa of the conjugate acid, that's -7, right? So Cl minus is a terrible base. HCl is a very strong acid. A strong acid has a weak conjugate base. The conjugate acid of Cl minus is HCl. That is a very powerful acid. This is a very weak base. It's still a good nucleophile because it's a big atom nucleophile. We'll explain why this is in a second. All right, an even more extreme example could be iodide. The pKa of hydrogen iodide is -10. Hi is one of the strongest acids known. I- is one of the weakest bases known. It is a great nucleophile because it's a big atom nucleophile. Iodine is in the first, second, third, fourth, fifth row of the periodic table, right? Its atomic number is way over 10. That's a good nucleophile. Something like thiolate, sulfur is in the 1, 2, third row of the periodic table. Its atomic number is bigger than 10. This is considered a big atom nucleophile. The pKa of a thiol is 10. And so remember, we set up this imaginary dividing line of pKa 14, and we said everything on one side is a strong acid and everything on the other side is a weak acid. So this would be considered this is not a strong base, but it's because the nucleophilic atom is a big atom, that is considered a good nucleophile. Okay, another example could be something like maybe something like this. Phosphorus, well, this guy isn't even anionic, right? It's neutral, but phosphorus is a big atom down there in the third row of the periodic table. So this would be considered a pretty good nucleophile anyway. So, and the reason for this is because big atoms are polarizable. They can distort their electron cloud. And because they're big, they can get in there and push the leaving group out. All right, so let's maybe draw a couple of pictures here to try to illustrate what's going on here. So here we have our substrate, and I'm going to junk this carbon up with 2 methyl groups, right? This is going to be secondary. And the nucleophile here is going to be And so this methyl group has big van der Waals radius, like that. And I'm going to use as my nucleophile the tiny fluoride ion. Well, the fluoride ion is small. It has difficulty getting into these, secondary carbon because it has to fight its way past these two big methyl groups. Okay, but now I guess kind of paradoxically, when I go to a bigger atom such as iodide, the situation changes completely because iodide is polarizable. Its valence electrons are far away from the nucleus. And so what iodide can do is distort, even though it's bigger, it can distort its electron cloud so that now it kind of looks like a baguette or something like that. And now it can get in much more easily than fluoride can. Fluoride is like a ping pong ball. Iodide is kind of like a wiffle ball that you can distort, and it can find its way into that substrate carbon. So the best nucleophiles for SN2 are anionic strong bases, but there are those two important exceptions we always have to keep in mind, that the nucleophile cannot be sterically hindered, and it cannot be, if it is a big atom nucleophile, it can be a good SN2 nucleophile anyway. All right, so let's look at some pictures where we're trying to put this on a quantitative footing. Okay, so on this slide, what I have here is I've plotted the nucleophilic ability of the nucleophile on the y-axis and the pKa of the conjugate acid on the x-axis. And so we have our little magic dividing line here between what is a strong base and what is not a strong base. And so what we see here is that as the pKa of the conjugate acid increases, right, we're getting a weaker and weaker and weaker acid as we go to the right on this diagram. We're getting a stronger and stronger acid as we go to the left of the diagram. That's what how the pKa is correlated to acidity. And so we see that as the conjugate acid gets weaker, the conjugate base gets stronger, the rate of the reaction, the nucleophilic ability of that nucleophile increases. So yes, all of these little data points didn't line up on a perfect straight line, but there is a trend. Stronger bases, the strong bases live on this part of the diagram. The stronger the base gets, the better the nucleophile gets. I know all of these points didn't fall on a perfect straight line, but there is a trend. But now when we look over here, let me see if I can make this a little bit bigger. So this is where the really strong acids live. But we see that these are very good nucleophiles because now we're into the second, third, and fourth row of the periodic table. So this is iodide here. It's this diamond here. That's iodide. It's an extremely weak base, but it's a very good nucleophile. Why? Because it is polarizable, big atom. And so this is bromine down here. This triangle is bromine. It's a big atom nucleophile, but a very weak base. And this square here, that's Cl minus. And this other square here, I believe this would be either sulfur or phosphorus, or not really sure what it is, but it's the second row. All right, so there's a trend here. The stronger the base, the better the nucleophile, but big atom nucleophiles are good nucleophiles regardless of their basicity. Okay, so that's about the leaving group. So we don't have to worry about that because we're just talking about halide. Whoa, that was wrong. Whoa. All right. Okay, so let's talk about, how about let's do some problems with the using this SN2. All right, what about something like this? Now I want to add sodium hydride to this. This sodium hydride, this is a very strong base, but it's not a nucleophile. What do you think is going to happen here? Well, that's a strong base. I'm looking at this molecule, and this OH, this is the most acidic proton in the molecule. What NaH is going to do is it's going to remove the proton from that alcohol functionality. And now what I've created here is a molecule that has a nucleophile at one end and a leaving group at the other end. It's the SN2 setup where I have a strongly basic anionic nucleophile. And when this oxygen atom can displace this bromine, and when it does so, I get a 1, 2, 3, 4, 5 member. What the hell is that? Oh, I swear, it's always something. Will the ghost of science 113 show yourself? Right. I swear, it's always something. You know, if they were to announce that an asteroid is headed for Earth, I would say, what took so long, you know? All right, so are we back in business here? Oh, dear Lord. Oh, God Almighty. Okay. Looks like maybe we'll be back in business in a while after this. So you know what just happened is that all of this, the projector just turned off all by itself. I guess it's just par for the course. Okay, looks like we're back in business. Okay, so I see that this thing can ring up to make a 1, 2, 3, 4, 5-membered ring. Oh, and this is something else that we should keep in mind is that we can have an intramolecular SN2 is possible if a 5 or a 6 ring can form. right? Those are our most thermodynamically stable kinds of rings. And so when the nucleophile and the electrophile are on the same atom, when the nucleophile and the substrate carbon are on the same molecule, and a 5-membered ring or 6-membered ring can be formed, then that is going to be a possibility. Okay, so before the ghost of Science 113 makes another appearance, we better talk about the other nucleophilic substitution mechanism, and that is the SN1. SN1. This one's not as useful as SN2 because this is a carbocation mechanism. And it differs from the SN2 in that in the SN1 mechanism, X leaves first, comma, then the nucleophile attacks. So at the very minimum, the SN1 reaction is 2 steps. The leaving group leaves first, and then the nucleophile attacks. So the SN1 is different from the SN2 in the timing of the events. All right, so let's look at an SN1 mechanism and SN1 reaction and write out the mechanism. All right, so we could have maybe something like this. Let's put the leaving group there. And now the nucleophile could be water. And what is going to happen here in the SN1 mechanism is the nucleophile doesn't get involved until later. What happens first is the departure of the leaving group to make a carbocation, right? And one of the reasons that SN1 is not as useful as SN2 is that whenever we're dealing with carbocations, we know that this may or may not rearrange. We don't have rearrangements in SN2 because we never have a carbocation in SN2. So that's the SN1 may go bad because that carbocation could rearrange, and maybe that's not what we were looking for. So in the SN1, this has left. It makes a carbocation. This is the slow step of the reaction because we're asking a molecule that where every atom has an octet to become something where an atom now only has a sextet, right? So this is going to be a slow step. And now the nucleophile gets involved. And in this case, the nucleophile is going to be water, and the nucleophilic atom of water attacks the carbocation in an intact manner. And so water has attacked. We get this oxonium ion. And now oxygen doesn't like to have a positive charge. It would rather be neutral or negative. And so probably the I- that was formed in the first step, he's functioning now as a base, removing the proton from that oxonium ion. And the final product here is going to be this alcohol. Okay, so SN1's is kind of an intricate reaction because it's going to be 2 steps. The leaving group leaves first, and then the nucleophile comes in. And so we see there are a lot of differences. That's just one of the differences between SN1 and SN2. All right, so let's talk about how SN1 differs from SN2 besides the fact that that it's two steps. Okay, substrate structure in SN1. Well, if we look at this mechanism, we see that departure of the leaving group creates a carbocation. So we have a very nice order of reactivity among the SN1 substrates, and it's going to be the exact opposite of what it was in SN2, because now what we're looking for in SN1 is the best reaction is going to produce the best carbocation in that first step. If the carbocation is super primary or primary, it's going to be way up here in energy. That energy, that first hill is going to be very, very high. If we can lower the energy of the carbocation, that hill is going to get lower. The reaction is going to be faster. So the fastest type of substrate for SN1 is going to be something that's going to give us a resonance stabilized carbocation, and then a tertiary carbocation, and then a secondary, and then a primary, and then a super primary. Never. Right, we never see an SN1 reaction on a primary substrate or on a super primary substrate because the energy of these carbocations is just prohibitively high. So effectively a secondary substrate is the most, is the end of the line when it comes to SN1. So we see that it's the exact opposite of SN2 substrate structure reactivity order. So maybe something like this. Just some concrete examples here. This guy here, when this leaving group leaves, when this Cl leaves, yes, I know it looks like a primary carbocation. I know it looks like a primary carbocation, but it's not a primary carbocation. It's a resonance stabilized primary carbocation. So this is very good. This benzylic substrate is very good for SN1. That's a resonance stabilized primary carbocation. But something like this, departure of Cl here to form a carbocation that is primary but not resonance stabilized, never. SN1. That carbocation is just too high in energy. So the substrate structure for SN1 is the exact opposite of the substrate structure of SN2. All right. Another way in which SN1 and SN2 differ is in the identity of the nucleophile. Nucleophile structure in SN1. So remember, for SN2, we wanted an anionic strong base nucleophile. And we needed that because in SN2, the nucleophile has to push out the leaving group. But in SN1, the leaving group takes off all by itself in the first step, because what is leaving behind is a carbocation that is stabilized either by resonance or by being tertiary, or maybe even by being secondary. So the typical SN1 nucleophile doesn't have to be a good nucleophile. And in fact, the typical SN1 nucleophile is going to be a weak base and they're going to be neutral. Right? They don't have to be anionic. They don't have to be loaded with a lot of electron density, because they don't have to push out the leaving group. So some examples here: is water a weak base? Oh my heavens, yes. Water's not a strong base. If water were a strong base, your hair would melt in the shower. If water were a strong base, your teeth would dissolve when you brush them. If water were a strong base, you'd take a dip in a swimming pool and your swimsuit would disintegrate, and then your skin would start to burn. So a typical SN1 nucleophile would be water, right? It's a weak base, it's neutral. Another typical SN1 nucleophile could be an alcohol, right? That's a weak base and it's neutral. Another typical SN1 nucleophile could be a carboxylic acid, right? Is a carboxylic acid a strong base? No, that's why it's called, you know, maybe it would be called a carboxylic base. So these are your typical SN1 nucleophiles. They are weak bases, and most of them are neutral. But the truth is so messy, right? But chloride, that's anionic, but it's a very weak base because HCl is a strong acid. Br minus, that's a weak base because HBr is a very strong acid, and this guy is anionic. Same goes for I minus. All of these are okay for SN1, principally because they are weak bases. So that's an important exception when we're talking about what an SN1 proton, what an SN1 nucleophile can and cannot be. All right. So how about let's look at the stereochemistry of the SN1. All right. So I have this data table here. More differences between SN1 and SN2. Stereochem of SN1, the carbocation can be captured from quote unquote above or below. Sometimes with equal probability, sometimes not, but this is something we have to keep in mind. The carbocation is planar, sp2 hybridized and planar. In SN1, the leaving group leaves, the carbocation can be attacked from the top or from the bottom by the nucleophile with more or less equal probability. So this is another reason why the SN1 reaction is not as useful as the SN2, because we get ambiguous stereochemical result. So let's look at an example here. So let's make this substrate, tertiary so that we know it's going to be SN1, and I'm going to put Cl there. And over here, I'm going to put a stick-up methyl group. This is an SN1 reaction. In the first step of SN1, the leaving group leaves. I have a tertiary carbocation that is sp2 hybridized and planar. And now the nucleophile, let's use water, weakly basic, neutral nucleophile, typical SN1 nucleophile. Water is going to attack. But this water molecule can attack from above or from below with more or less equal probability. So what I get here is one situation in which the water molecule has attacked from above, shoving that pre-existing methyl group down to the bottom. And then I have another situation where the water molecule, the nucleophile, attacked from the back, shoving that pre-existing methyl group up on a wedge. See, so the carbocation was attacked from the top and from the bottom, from the back or the front with more or less equal probability. Okay, and so now the Cl minus is going to come in, functioning as a base, removing that proton. We get HCl as the inorganic product here that we really don't care about. And we have this alcohol in this case. And over here, the Cl minus is going to come in, remove this proton from this oxonium ion. And with the second situation, now the product is going to be this. Okay, so tell me in the chat, how are these two guys related? Did we get one product just drawn in two different ways? How are these two related? Anybody giving it a shot? Oh, yes, thank you. They're diastereomers, right? The reaction is a disgrace. These are diastereomers. And remember, diastereomers are totally different compounds. They have different melting points, boiling points, solubilities, delta H's of formation, delta G's of formation, different retention times in a chromatography experiment, different NMRs, different IRs. These are totally different compounds. So this is pointing out yet again why the SN1 is not as valuable as the SN2, because I got here two totally different products. I don't want that to happen in the laboratory. I want 100% yield of one product. So this SN2, because of that carbocation, can not only undergo a rearrangement to give me something maybe I didn't want, but even here where no rearrangement happens, I'm going to get diastereomers, two totally different compounds. So SN1, not as reliable, not as good as SN2. Okay, so let's see. Let's just finish up in the remaining couple of minutes. How about let's write a mechanism. Let's write out a mechanism that involves a carbocation rearrangement in SN1. Okay, so I'm going to put Br there. And I'm going to react this with methanol. The product is this, plus HBr. Well, I guess if I wanted this rearranged system, this succeeds brilliantly, right? But maybe that's not what I wanted. Maybe I just wanted to kick out this BR and put CH3O where this BR used to be. I didn't get that, right? So again, underscoring why this is, why SN1 is not as good as SN2. First step, departure of BR minus to give a secondary carbocation, not the greatest carbocation imaginable, but it's viable. At least it's not primary or not secondary. Okay, now it's time for the rearrangement. This is carbon 1, this is carbon 2. Something bonded to carbon 2 pulls out of carbon 2, plugs into carbon 1. The charge moves from carbon 1 to carbon 2, and what pulled out is the dot. So there's the dot. He pulled out of carbon 2, he plugged into carbon 1, and the charge moved from carbon 1 to carbon 2. So we're going from a secondary ion to a tertiary ion. All right, now to finish this up, now it's time for the nucleophile, the methanol, to get involved. It attacks the carbocation. And then with a positive charge on this oxygen. And then in the last step, that Br minus that was formed upon departure comes in, big arrow, removes that proton, and the oxygen gobbles up the electron pair. So this is just an example of a carbocation rearrangement that happened in the course of an SN1. Okay, going to stop there now. Over the weekend, I'll be posting the study guide for the final exam and be sending out all kinds of messages dealing with the lab and also pre-final exam activities. Anything I need to know about, tell me in the chat before we leave. You should have gotten a message from Gradescope saying that the lab quiz average was a 65, and you should have gotten a message from Gradescope saying add 10 points. All right, so the SCH3 is that in the examples I gave you, it was always SCH3 minus, right? It was never HSCH3, so there was never any dissociation. If I had used HSCH3, then there would have been a step, you know, if this were S here, it would have been exactly the same mechanism, except swap out the O that I've written here for an S. Oh, yeah, this is wrong. That should have been here. Is that what you mean? Chung, chung, chung. Yeah, sorry about that.